Hello everyone, this is the video lecture for Calculus 3 using MyMathLab. We are going to do the last four sections of the homework workbook stuff here together because I just don't have enough time in class. So I'm going to try to make this streamlined, and then we can ask more questions in class, etc. Now, I think I already did this some of the section, at least some of it, but you never know with the audio quality of the other ones. The main thing is that we're going to be doing this formula here. I already deleted these from the homework because they were not pertinent to the rest of the section. I mean, it's cool for the other sections, but whatever. So we got rid of them. So let's do this guy right here. And again, I'm pretty sure I've already done it, but, well, here we go again. I'm going to move this guy over so I get a z. And that z is what we're going to use in my surface area formula. Now, please excuse my terrible handwriting. I'm using a very small tablet, and it's kind of unfamiliar to me, so we're going to figure it out. There's your formula, double integral of z sub x, z sub y. Here we go, already got it. So my derivative in terms of x will be a negative 2x. So when you square it, you'll get 4x squared. Same with the y, 4y squared. Don't forget the 1, because I forgot the 1 many times. Dy dx. We need to find the area for where this is happening. Now, if you go back, this is actually a upside down parabola that's going down here. And it's stopping at z equals negative 20. So we're looking for basically the area of the bottom ring. So I'm setting this whole thing equal to negative 20 essentially. Move it over. So we got x squared plus y squared is equal to 20. And so basically the radius is square root 20. Because it's, radius stuff, I'm going to go to polar form. So we're going to go 0 to square root of 20. And then notice here, this will be 4r squared plus 1. And then we have to have the required r dr d theta. I really do want to say just toss it in to Desmos on most of this stuff, just for speed's sake. And so what I'm going to do is pull up Desmos and do this thing. And we're just going to go and try this thing out. Now, I have like the paper copy of what I've been working on with me, but it's all kind of clunky, so we'll see. Like, I've done all these problems already. I just want to make sure that we do what we need to do to get it done, and then we can move on with our lives. So we got this thing, but as you know, everything's going to be with a pi in there, right? So divide by pi essentially, and we can change that into a fraction, and that's exactly the answer, 364 over 3. So this is 364 over 3, and then there's a pi. And that's how I recommend doing these at this point, because we can use Desmos graphing. Just do it. Just do it. Now, there's going to be some that are more difficult than others, and that's fine. Let's analyze them as we go. But I'm not going to waste your time on this. Let's keep moving. So next one. Surface area of this guy. Now, this one is not one of those that you could just say, oh, you just put that in Desmos. But it is equally easy. So I need to find my z by itself. So I want to actually... Oh, no. I want to draw. You're going to let me draw? You're not letting me draw. There we go. I'm learning this program too. So move this whole 2z over and then divide by the 2. And so you get x squared minus 6y all over 2. And that's going to be the thing that I take derivatives of. It might be easier to do this here. That way I could start taking derivatives individually. Notice where this region is. So we're talking 3x, which is kind of steep. And we're going from x equals 3. But then I think that's going to be a y equals 1. Hold on. No, because that'd be a 9 actually, wouldn't it? So because if you see here, we got 3 times 3 would be a 9. I don't know if it's going to matter, but this is the little triangle area that we're talking about down there. All right, here we go. So double integral of the square root of, take some derivatives, the 2 comes down, gives you a regular x, square it. And then we got this guy here. It'll be a 3, so 3 squared is 9, regular 9. And then that's dy dx. Now, I'm not going to polar form because no way here, no need for that. Oh, gosh, I've already forgot it again. Is there an erase button? Is this what it is? That's not an erase button. This looks like an erase. No. Well, just don't mess up, Chad. It's a 10. Why is it a 10? Because I needed to have the plus 1. Didn't I already say that? And I still forgot it myself, even now. Okay. And I have it right in front of me, and I still forgot it. It's like the answers are right in front of me. So let's focus on this triangle here. I'm going to go from 0 to the 3x, 0 to the 3. So I don't even need to figure out the 9. I'm going to go to Desmos and be disappointed. It's not going to come up really nicely here. I'm forgetting something else. No, I'm not. Actually, I'm not. Here's the thing. I want to integrate this, but it's like, I can't integrate that. I need something on the outside to make it work. Well, it's because it's dy first. So we're going to integrate this in terms of y first. There's no y. You add a y, toss in the 3x, etc. There we go. Now, use substitution. du is 2x dx. And so then I'm going to divide by the 2 essentially. And so then that x goes away with it as well. I mean, this is all like very, very fast math. Nope, it's 1/2. 1/2 u du. So add 1 to the power, divide by the new power. That's going to be a 3/2. And then I got my x squared plus the 10 to the 3/2 from 0 to 3. If I plug in the 3, I'll get 19. Yeah. Oh, and these all cancel, by the way. I get 19 to the 3/2. And then if I plug in the 0, I get 10. And actually, that is the answer. My math lab has it as 19 square root of 19 minus 10 square root of 10. But either way, it's all good. And you can see why Desmos would not have helped us here. It's not polar form, so I can't just divide by a pi. Or, yeah, I can't just divide by a pi. Keep going. So this guy here, I feel like I deleted him. Anyways, moving on. So move the z over, and I got all this stuff here. It's really not a hard problem. It's just kind of different. So notice that we have a rectangular region over here. So that's kind of easy. Let's do this thing. So I need the square root of my derivative in terms of x, so that would be a 2x, and then I have ln makes 1 over x, and then nothing else, square it. And then my derivative in terms of y would just be the square root 39. So square root 39, it's squared, so it's just going to be a 39. Remember the plus 1 dy dx. This is super easy for rectangular regions, so there we go. We got a plus 40 essentially here. This thing here actually starts to cancel out. When you FOIL this thing out, and you will have to do this by hand because the answer is like ln of something or other. What you get out of that is 4x squared. And when you multiply these together, you get 10, just 10. But then there's 2 of them, so it's actually going to be 20. And then squaring this guy, you'll get 25 over x squared. Remember the 40 that you have, dy dx. So these make a positive 20, but notice that what's happened here is that you had a negative 20, and now you're replacing it to make a positive 20, and so it can actually work backwards from what it was already. This is a little trick that I don't know if we've seen this back in like Cal 2 or something or other, where it basically does the same thing it just was, but with a plus instead of a minus, means that it's actually squared, but with a plus sign now. That's okay. Yeah, double integral, there you go, dy dx. If you can't see it, I mean, it's probably because of my handwriting, but what happened is I had a minus, now I have a plus. That was it. But because it's all alone now, square and square root will cancel, and so we're left with the 2x, 5 over x, dy dx. Cool. And so what we want to do here is just integrate normal stuff. So I don't have a y. I toss a, I have to have my limits, right? Oh yeah, for y it's just 0 to 1. So that just goes away. You essentially just make it go away entirely. So that was kind of easy. This one is x squared, and then this is going to be a 5 ln x from 1 to 2, and this is where we plug it all in. So I got a 2 squared is 4. When I plug a 2 in here, I get 5 ln of 2. Plug in a 1, we get a 1. Plug in a 1, we get a 0. And so then these make together to make a 3, 5 ln of 2. And that is the answer. Awesome. One more in this section. So this one's actually pretty cool. I'll show you how this call kind of like works out, but this little hint here kind of helps out like a lot. Before we keep going, I want to show you how we need to do this. This is a circle, but this is an ellipse, and how this works is you could rewrite it like this. It's a classic pre-cal type of thing where the 25 and the 16 make the 400, and so then basically you're man, it's only 5. It's only 5. It's not 25. So the so the 25 and the 16 make the 400, and therefore it's kind of just basically divided by their opposites. This one had a 25, now it has 16. This one had a 16, now it's 25. But again, because they're squares, etc. So that's my ellipse, and basically if you're going to draw this is a radius of 2, and then we have like an ellipse kind of like this going around it. It's a little bit bigger on the y. You can see that's bigger on the y. And so they say, go, figure it out with this cone thing. So we're going to have to do double integral and do some derivatives with this cone thing. So I want to just go like z sub x on the side here, and then you'll see how it's symmetric for the y, so it won't be too bad. 1/2, leave the inside alone, negative 1/2, 2x. We've done this a whole bunch. The 2's cancel, the x is in the top, and so what we get is x plus y all over the square root of x squared plus y squared, and then remember the plus 1, dy dx. Now, obviously, this looks like it's going to go to polar form anyways. This 1, though, it's kind of interesting. It's going to pop up in the top as kind of like this square rooty thing. I think we're going to figure that out. Oh, no. I did one thing wrong. I did it all wrong. Hold on. We don't simply add them. We have to add their squares. So it's the x squared plus the y squared, and then we're saying divided by x squared plus y squared. I jumped ahead. There's got to be a eraser somewhere around here. Is there like, can I like erase? Oh, if I just tap it. No? Okay, can I use my mouse maybe? Would the mouse be better? I'm learning it too, man. I'm just trying to figure this thing out so we can get this thing done. The mouse is not doing any better than my little drawing thingy, but hold on. Hold on. We're really close. Okay, and then I'm going to leave it. I don't care. Okay, so sorry about this. Let's start over. What we're doing is I'm squaring both of them, right? It's the derivative squared. So it actually looks like this. And then again, plus 1. So I was off a little bit right here and on the bottom as well. Because you're squaring your derivative, the square root in the bottom goes away, and then you have a squared on top. Notice that because you got the top and bottom, what's actually going to happen, the whole thing, I believe, is going to turn into a 1. So we got x squared plus y squared over x squared plus y squared dy dx. And what you can hear is a 1. Everything cancels, makes a 1. So you got basically square root of 2 dA. And this is the big, this is the hint part, where I'm looking for the area, but just multiply by square root 2. Sounds easy. So I'm going to say square root 2 times area. Well, we have an area of our ellipse, and then we have the area of a circle, obviously. So square root of 2 times, and then we got pi AB, so that would be the 4 and the 5. and then minus pi r squared. The circle was a 2 radius. So we got 20 minus 4 is 16. So we got 16 square root of 2, and then put a pi on it, and that is the answer. So we didn't actually have to keep integrating. Cool. Okay, so since I'm on a roll, I'm going to just keep on going to the next section right quick, and we're just going to stop when we stop and do the next video. By the way, blah, 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 blah. This is actually kind of important. We might come back to that later. But really, for the main focus of this section, it's going to be this guy. Notice it's the exact same as the last one, except that we have this G function thing going on, okay? So it's surface integrals instead of surface area. We're just doing surface area with a little bit of change in there. Not big deal. I am going to use this a little bit at the end, but not extensively. I'll show you in a bit, okay? So let's do some of these guys, and some of them are already deleted, but I'll show you as I go. So it says just integrate. Now, we're talking about a sphere here, and it's the surface area of a sphere, basically, but then I'm multiplying this as if it's a density, okay? So consider this kind of like a density for the surface area of a sphere. That's kind of what's going on. Now, the problem is that they don't say the top end. It's this, like the whole sphere. So I actually have to do the top and the bottom individually, like two separate integrals. Or because it's symmetrical about the z, like z doesn't matter, then the top half and the bottom half should be the same. And I'm just going to double it. So essentially, in the end, I'm going to say double my g thing, my density times, and then I got my surface area just like I normally would. The problem is here is that we need to get this stuff over here and then square root it. And so my z is equal to the square root of 1 minus x squared minus y squared. And so when I start doing my derivatives of that, it gets a little clunky. So derivative, and then I'm going to square it. So what I'm going to do, because they're the same, like they'll be the same x's and y's, you just change the letter. I'm going to go ahead and take the derivative right now. So I got 1/2 on the front, leave the inside alone. Negative 1/2 power, and then minus 2x for the top. Notice that the 2's are going to cancel, negative in the top, square root thing at the bottom. But because it's negative and it's going to be squared, doesn't matter, just cancel. So I'm going to say x squared divided by 1 minus x squared minus y squared. Same thing for the y's. Plus 1 dA. I don't know. We'll figure that out later. I don't really care. Let me verify that I'm going to do this right, because I have it written down. Yep. That looks fine. Yeah, it looks great. Okay, cool. So notice that we have this x squared, y squared thing at the top going on here. But this 1 is really going to help us here. Of all things, that 1 is going to help us, because what I'm going to have is x squared plus y squared plus 1 minus x squared minus y squared. Because the denominator is this whole thing, I'm making this 1 into this guy, if you could see it. Making it into this guy. And because now they have a common denominator, I could just kind of mush them together. Well, watch this. Wham, 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 wham. Oh, wait. Y squared. The little things. So I got 1 over all the stuff. And that 1 can come out of the square root, I suppose. And we're left with this guy now. dA. We'll figure that part out in just a second. What I did is I said, polar form. No. I didn't just do polar. I think I did something more than that. No, I did polar. Yeah, I did polar form. So let's do that. I got 2, double integral, and so this y squared turns into not rho, it's r. R squared. No. Yes, r squared sine squared, because y is r sine theta. Yeah. But we also have the required r, and then we have this thing right here, and that's going to be 1 minus r squared essentially. dr d theta. Again, I already have my required r. If you're doing a sphere, then you're going to go from 0 out to the radius, and the radius is just a 1. And then for the theta is 0 to 2 pi. Okay, so this is what we got going on. You know that we're going to end up with polar, pies and stuff like that. So I'm going to recommend Desmos for this one. I did it by hand, but it was a little eh. So 2 integral 0 to 2 pi, 0 to 1 of r cubed, technically, sine theta times 1 over the square root of 1 minus r squared, dr d theta. Did I make a mistake somewhere? What is it trying to tell me? Oh. Okay, well, it really wants that. 0? That's not what I got. Give me a second here. It's definitely not 0. I might have mistyped something here. So r cubed. Oh, sine squared. It's sine squared. My bad. There we go. And then you already know there's going to be pi's. So 1 divided by pi. And then you can see what that is as 1.33333. If you really, really want to know what that is, and yeah, 4/3. And that's the answer. So essentially, go to Desmos, 4 pi over 3. Great stuff. I did it by hand. I could show you by hand. I have it all written down, but it's actually kind of long. Not needed. Not needed at this point. So let's do some more. Same copy paste here. Same style. I did all of these by hand, by the way. So yeah. Okay. So I'm gonna stick this thing at the front, and then we're gonna integrate like surface area just like normal. So 6x square root of 17 minus 8z, and then times the square root of, and then some derivatives. Well, notice that in terms of x, I'll have the 4x squared, or the 4x, and then I'm gonna square all that. So 16x squared. 16y squared, and then don't forget the 1 dy dx, I guess. Cool, cool. At this point, we are really close. In fact, I think I would recommend Desmos as long as you know what you're doing. So let's just like make sure we're understanding here. We got z is greater than 0, so you plug a 0 in there, and essentially, and you're wanting to know what this kind of looks like. I would say also move this stuff over, and so what you kind of get here is 2x squared plus 2y squared is equal to 2. Get rid of everything that's a 2, because you don't need that. And this is our circle. So we got a circle from 0 to 2 pi and 0 to 1. Right? Because it doesn't work. It's dy dx. I would still think of it like a circle, though. So here's what I'm going to do, because I'm going to be silly with this. If you want to solve for y, you could say it's a negative square root of 1 minus x squared, and then the positive square root of 1 minus x squared. On the top and bottom, I'm going to go negative 1 to 1. And now it's a circle, but it's all in rectangular. And I should be able to put it all in there. Now, note that it is a circle. So we are expecting pi's in the end, even though it looks a little weird. And that is okay. We are going to figure this thing out together. I'm just kind of, copying what we got there now. So this was a 6x squared times square root of 17 minus 8z. Hold on. Oh, there's a z. Okay. I can't put a z because I need a dy dx, right? So I'm going to replace that z with what I was already solving for over here. Well, it's right here. There it is, z. So 2 minus 2x squared minus 2y squared. Like a direct copy paste in there. So 2 minus 2x squared minus 2y squared. And then still times the square root of 16x squared, 16y squared, plus the 1, all this dy dx. And again, I'm expecting this to have a pi. There we go. It's beautiful. There we go. And that is the right answer. We're good. Cool. So 35 over 2 pi. Done. All good. Okay. Keep cruising. Next guy. Now, this one's a little tricky, okay? So I'm kind of having to explain a tiny bit about what's going on because we have this f.n d sigma blah, blah, blah. What we're really wanting to do is going to be, in the end, an f dot, and this will be ru cross rv, and then du dv. This is kind of what we're wanting to do. If you go back up to our formulas right here, you can see that's the flux formula. And then what are they wanting here, right? They say flux. So we are using that. But we can kind of get around it a little bit in this case. What I'm going to do to kind of cheat the system is I'm saying that u is equal to x, and v is equal to y, and everything kind of just works itself out. It's really nice and pretty, okay? So what we need now is my f, and then I need this cross producty thing, okay? So let's work on my f. It is right here, okay? Now, I'm going to have double integrals, so basically in the end, I need to get rid of my z. So you can see those z's are kind of a problem. Good thing I have a formula for that. So I'm going to say 1 minus y squared, squared, and then comma x, comma, and then minus 4 times 1 minus y squared. So that's my f right there. Now I need this RURV thing. What we're going to want before we keep going here is basically I need to like take derivatives of this thing in terms of x and y, blah, blah, blah. It's actually kind of silly. I'm tempted to just not show you, but what's happening is that I'm going to have this cross this, and I've got basically my x's and my y's, and they say go figure it out, and you can guess it's going to end up this way. So what I'm going to have now in the end is double integral of this big thing, dot 0, 0, 1 d u dv, I guess. I don't know, dx dy. I like dx dy. That's what we're using. Or dy dx. It doesn't really matter. Well, blah, 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 blah. The only thing with a dot product is going to be these last guys. So you're essentially just using this one here. It's much easier, much easier. So I got -4, I got 1 minus y squared, and then we got dy dx, or whatever you want. Cool. Yeah, that's basically it. Now, the only thing is we need these limits now. And this is where it gets a little interesting as well. It says that we have this parabolic cylinder, and what they mean by that is we have like a parabola and another one, and it's like making a tunnel. It's like making a tunnel here, okay? So that's that we have a tunnel, and they're wanting to go from x equals 0 to x equals 1. So basically, like just this part of the tunnel right here, that little tunnel area right there, and z equals 0 is the bottom. Okay, so we have a little tunnel right there, and that's it. So we're wanting the shadow of what that would be like. And so if you make this x and y, what you actually have, and you got to be careful here, it goes into the negative. It's in -1 and +1, and this is only 1 over here. The reason why it goes negative positive is because you can see it's going into the negative and the positive, and where is it colliding with the xy plane is at 1. So this is the top view of our tunnel, and that's going to be the surface that we're going to look at. Thankfully, that is rectangular. So I can say down here that I'm going to go -1 to 1, 0 to 1, and integrate. Now, again, I did all this by hand. Actually, I didn't. This one I did in Desmos. I could tell because I just stopped. That's okay. 0 to 1, -1 to 1 of -4 times 1 minus y squared dy dx, and that is perfect. That is perfect. -16 over 3. They're going to want the negative, which is important, I guess. Kind of. There you go. Yay! Next one. And I'm going to tell you ahead of time, this is the last one. I already deleted this one from the homework. So we're just going to focus on this guy and be done with this section. So, same style, but we're going to have to use a little bit more math here in a second. So we got a cone, and we're going from planes z equals 1 and z equals 2. So it's kind of like this, and then like our origin is kind of like down here. So we're looking at this kind of cone right there, and I want to set it up. So how this is going to work is a little bit more involved than the other ones. And I actually did have to go look this one up to kind of get a clue as to what to use. But we're going to have to say that x is equal to r cosine theta, y is equal to r sine theta, which is perfectly fine. If you look around, my z is equal to an r. Okay, so we already have everything we need. And what we're going to have to do is take derivatives of this stuff here in terms of r and theta. Okay, so how is this ultimately going to work? Well, we have a double integral of my f. I'm going to say dot, and this is that RU cross RV business again, du dv. Well, I'm saying that it's not u and v, it's r and theta. So you can put an r there and a theta right there, and everyone's happy. So let's do that. We have to find this part first, and it's a little bit more involved than the last one. So what's my derivative in terms of r is going to be a cosine. Derivative in terms of y is going to be a sine. And derivative in terms of r here is a 1 cross. And I'm going to do this all in terms of theta. So my cosine goes to a negative sign. My sine goes to a cosine. And then this guy has nothing, so he's just 0. So I'm going to find this cross product on the side now. Always start with the 0. Cosine times cosine, so we get cosine squared. That's a k. And then I got 0. I got this is going to be a negative k, so it actually ends up being positive in the end. Still sine squared with a k. 0 always in the middle, and a 0 over there. 1 times this, so over here, this is a positive j component. So I'm going to retain the minus sign. And again, just 1 times it, so that's a j. And then this is a negative I component. So I'm actually going to keep a minus in the front now. That's an I, and then a 0. So ultimately, this thing is going to end up being, I got negative r cosine theta, negative r sine theta, and then I have these things kind of added together. If you notice, it's sine squared and cosine squared, so it's just going to be an r, because like those turned into a 1. So yay, we got that thing there. This is the vector. This is this part, this vector here that we're going to be dot producting it with. So one last thing, I need to convert my f into polar form stuff. So notice that we have an x, a y, and a z. I actually have to convert them using these same formulas here. And so it's going to be a little bit extensive. I got negative 3 times, and then I got r cosine theta, and I got a comma. Yeah, because this is a vector. Yeah, this is a vector, comma, negative 3 r sine theta, and then z squared, it's going to be r squared, dot with this dude. Just repeating it here. Okay, cool. We'll figure out the rest later. So when we dot it, it doesn't all just cancel. Darn. So a little bit more than last time. So dot product, though, ultimately isn't that bad. I'm going to mush these two together. So I'm going to get a negative 3 r squared cosine squared. And then, no, it's not negative. It's positive now. Positive 3r squared sine squared. And then an r cubed. And now, because I know this is polar, you're going to say, oh, I need a required r. This was the required r. This is your r that we would normally use for the required r. So do not add an extra one. I tried it. It didn't work. No one was happy. So just don't do it. Now, finally, we need to figure out like what we're doing. Now, this is r equals, and then we got our theta. Oops, that's not what I want there. And then I got my theta. Theta's easy. It's 0 to 2 pi. That's pretty basic. But what are my radiuses? What are my radiuses going to? Well, because we have r is equal to z specifically, I'm just going to go from 1 to 2. So from 1 to 2, Desmos, here we go. And I believe that we should be able to get it with the pi's. So this one is what I'm typing in. So let's try that. I got integral 0 to 2 pi, integral 1 to 2 of, and then this is 3r squared cosine squared. I know that like this is all going to cancel and make a 1. I get it, but I just probably should have done that just so it's like faster. That's fine. That's fine. It happens. And then I got r cubed. And then I'm going to do dr d theta. And again, I'm expecting it to be 1 over pi of some kind. And that is beautiful. So negative, no, it's positive, sorry, 43 pi over 2. And that's my answer. And they're going to go, it's wrong. No, it's not. They want a negative. But here's the thing, like, what they did, like, I went and looked. They switched this. This was my derivative in terms of r, and this was in terms of theta. They just said, let's do the theta first and then the r. So what you're doing here, you're literally just putting a minus sign in the front of this vector, and so therefore a minus sign all the way down. And how is that supposed to be any better? I don't really know. But if you go back up to this flux formula, I have a reason to admit that mine is right. They have a plus minus right here. So there's no way that technically they shouldn't accept it. So try the positive. If it doesn't work, just be angry, put a negative in, and there you go. But that's it. That's the answer. I'm going to put a plus minus just to kind of like fight the system. You know what I mean? So there you go. I'm happy with it now. Cool. I'm actually, because we deleted this one, I'm going to stop the video recording for this one, and I'm going to jump to the next 2 sections for the next video. So thank you very much. Have a great day.